let's start with the analysis. I'm going to share my screen. Oh, here we are. So let me see in the chat, we have something. Okay, yes, they just told me that the videos of the Monday's webinar are on YouTube. So you can already go and check them. And as soon as I finish this webinar, I will also put all the input files on our website. Okay, so you can see all the input files we've done yesterday and today by the end of this meeting. And now you can already access the videos of Monday's webinar on YouTube. Okay, so we just did the sequential analysis, and as you can see, everything went correctly. It took most 3 iterations for each step, and it took more than 10 minutes, okay? As you can see here, 800 seconds. Now we are going to see how much does it take in the parallel version. Of course, here, if you update this one, you will update the curve. Of course, during the analysis, I could have pressed update, and I would have seen the graph updating interactively. And in fact, now we will do the same with the parallel version. So keep in mind, 827 seconds. And now we are going to see how much does it take with 8 processors. So let me see the timing. With a single processor, it was 872 seconds. Then we are going to see the speed up with the parallel version. Okay, so let's say you have everything ready. We have an extra 827. Yes, T1 equals 827. Okay. Okay, now whenever you have a model that is already built for sequential analysis, it is very easy to convert it for OpenSeesMP. So if you recall, I told you that you have two parallel versions of OpenSees, OpenSeesSP and MP. Now, I'm not going to talk about OpenSeesSP because it is very simple to use. You just take the input files that you have here, and you just have to change the solver in the analysis steps from, let me see, where is the solver here? Actually, it is not this one. It is the one that we are working on now, which is this one. As you can see now, everything is not partitioned. Instead, as you can see here, everything is built on a single processor. And if you want to use this one in parallel, you can simply run the analysis with OpenSeesSP just by specifying the number of processors and changing the solver, where we use the UMF pack to the mumps, like in this place here. Okay, but as I told you, that approach has two drawbacks. One is that the entire model is first built into a single process and then split by OpenSees and sent to the other processes. So the first drawback is that you have a bottleneck in the first time when you build the analysis, because the build of the model is not done in parallel, it's done in sequential. The second problem is that since OpenSees needs to send different parts of the model to different processes, it calls an internal method of each element of each material that needs to send their data to the other process. And I've seen that in OpenSees, many materials and many elements are not implementing that method. Why? Because probably the developer who was developing that material was not interested in parallel processing, so he didn't put the code necessary there. So the main problem with OpenSeesSP is that you don't know if you can run your model in parallel, basically. The nice thing is that of OpenSeesMP is that you can run everything in parallel. The problem is that you're not able to write a parallel version of the TCL script. And that's where STKO can help you. Here it is very easy. You just need to change a couple of things in the analysis steps, which is very easy. In every, you don't need to change anything except the analysis command. So here we have two analysis commands, the vertical and the pushover one. So let's take the vertical first. You need to change the number, which is basically an object that reorders the system of equation. So instead of using the reverse cut tool make the number, which is the RCM, you use the parallel RCM. There is only one, so you cannot make mistake here. The only one that starts with parallel, okay? And then in the system you have two things that can go in parallel, which is the mumps and the parallel profile SPD. Now, profile SPD, it's almost never used because you need to make sure that your matrix is profile and is symmetric and positive definite. There are very few cases in which basically the linear cases are symmetric and positive definite, or cases in which you use plasticity with just strain hardening, not softening, and without, for example, non-associated plasticity. For example, you cannot use the rotational method because it generates non-symmetric matrices. So you need a parallel solver that is non-symmetric, and the only one is the mumps. So keep in mind that every time you need to change from sequential to parallel, you need to change first the number and then the system. So number, parallel, and system mumps. The rest will be equal. So we do this in the vertical analysis and then in the pushover analysis. In the pushover analysis, you need to do the same. So parallel number, this one, mumps, solver, and here you need to do an extra change because this one is a displacement control analysis. Well, the previous one was a load control, and the load control is the same for sequential and parallel. But whenever you have to do displacement control analysis, you need to change it from displacement control to parallel displacement control. Why? Because the displacement control needs to control the displacement of a node, but a node is not necessarily present to every process. That's why there is a dedicated integrator for this, which is called parallel control analysis. So we just go and select once again the node control. The degrees of freedom will be the number 2, so in Y. And the increment was 0.35. Okay, and we are done. We press OK. We don't need to change anything else. We just need to partition the mesh. So in my case, I have a single process with a single processor, single CPU, an E7 with 8 processes. Of course, I think you are all aware of how to see how many processes you have, but you can just go here on the CPU. You see the number of threads here, logic threads, or you can just change the representation of each process to logical processors, okay, like this. In my case, I will use all 8 processes because basically I'm not using anything else. So you go in partition and you choose the number of partitions. In my case, 8. Then you press partition. This is just a preview of the partition. You need to click done to accept it. Okay, for example, if I'm not fine with this, I can press 5, then we do the partition. Okay, now in my case, I want to select 8 partitions. I click partition. I have a look at more or less how many nodes and elements I have on each partition. The entire mesh is 15,000 elements, and here I have about 2,000 elements for each process. For me, this is fine. I click done. Okay, now I'm done. I can simply save the file and run the analysis. Now let's see how. Oh, of course, I have to change from OpenSees to OpenSeesMP. That's obvious. Then I can run the analysis. And then, as I told you, we just wrote the. Oops, I don't need this one. Okay, now basically when it starts, as you can see how fast it is. Oh, we just need to do one extra change. Let me. In the custom script, I told you that this script was made for parallel. Then before that we were doing the sequential analysis, I had to manually set the process ID to 0. But in this case, we are in parallel version, so I can get rid of this line because the process ID will be set automatically by OpenSees. Okay, okay, and save. Okay, let's run the analysis and let's see how long does it take. Well, it will take 2 minutes, so we can wait for it. Okay, the first step has been done, and now it will start with the horizontal analysis. As you can see, it's much faster than before. It was taking about 10 seconds each step. Now it is much faster. And here you can update the graph. If you remember, I just, in the script, I was writing this file, and here I can update it step by step, okay? Okay, let's let it run. Let's see how much does it take. Oh, we are 50% of the analysis now. And you can see, of course, how much processes it is using. It is using 100% of the old processes, as you can see here. We're almost done. Okay, that's all. So it took almost 2 minutes, which you can see here. I think we have some questions there. Okay, we have a question. How does OpenSeesMP treats the control node? If the control node falls in partition 5, let's say, the convergence has been checked instead. No, the convergence is synchronized between all the processes, of course. Otherwise, it will be impossible to run parallel analysis. This is for sure. Okay, so 2 minutes against, it is. So the T2 is equal to 1 seconds. So the speed up, you can say T1 divided T2. It's about 7 times, okay? Now, it is not exactly 8 times, because of course parallelism is not like magic. I mean, I use 8 processes, but there is a small overhead of using parallel computing. So it is not exactly 8, but as you can see, it is much faster than the other. So now we can go and see the results. Open database, and we can open this one or the other that we're just running now. This one is the one that I sent you. The one that I'm running now is this one. Okay, so this is our shell. By default, we go with the deformed shape. Now we can delete this plot and see the surface color map. Okay, by default, you have the displacement. Okay. Well, probably when I was constructing the model, I did something different. You can check the correct file that I sent you before, because here I see an asymmetry. Probably I missed, or I misdrawn some elements. In fact, as you can see here, the graph is slightly different. Okay, but I think it's because I misspelled some of the parameters. In any case, you will have the correct file, which is already set for the parallel version in the folder that I sent you, that I will send you. Okay, so let's go to the, okay, we can see at first the displacement. We can increase the deformation to 10, so you can see what's going on here. I like to switch off the mesh edges so you can see actually what's happening. And I need something else. I need, okay, this is fine. Let me change the displacement to this color so you can see actually what's going on. So as you can see, here you see all the failure lines. And the nice thing about this kind of shell element is that if you have a look, you probably would expect a bending failure. This is an overall bending failure, but actually what is failing is actually in the out of plane shear. That's why at the beginning I told you, look that if we use the thick shell, the results will be fine, like this one, because when this one is failing, even if the overall failure here is an inch, for example, about this line, what is actually failing is the shear failure of these mortar joints, same as in this case. In fact, if we go and check the damage pattern, we will see that the bricks are almost never damaged. Like, let me show you, for example, the maximum deformation on the section forces, and we see the maximum in-plane deformation. So it will give us a measure of what's failing in the in-plane direction. Everything is focusing on mortar joints, like in this case. As you can see here, these are the results of the shells. Otherwise, if you want to see what's going on in the fibers, you can just create another plot and create a beam shell fiber color map. And in the beam shell fiber color map, you will actually see an extrusion. So if I go in the front view, you have actually a series of points directly inside the at the position of the Gauss point. But then if you turn around, you see that there are many points. Why? Because for each Gauss point, you have many fibers, the fibers defining the cross section. Okay, and you can see here that the damage is basically entirely on the mortar joints. So let me show an animation of section fiber damage. I want to change this description to hot. Okay, and you can see actually what's going on here. Okay, so while you see an overall bending failure, what is actually failing is in the out of plane direction. You can see also this thing from visualizing the strain tensor directly on the fiber color map. For example, if I choose the vector plot and I choose to visualize not the displacement, like in this case I'm plotting the displacement, but if I want to plot something in the fiber, I can use the section fiber strain. For example, this one. One will be for the brick, and the other for the mortar. I will choose the mortar one, this one. Okay, perfect. And let me go ahead and I will show you the main failure lines. Okay, when you start from here, the failure, and we're going to see it from upside. Okay, at the very beginning, let me go here. At the very beginning, you see the strain are basically aligned with the shell plane. It means we have mainly in plane deformation, plane stresses, okay, which is typical of a plane stress analysis. But then as soon as everything starts failing, you see here they are still in plane, but you start seeing some transverse shear, as you can see from the principal vectors. And then when we go ahead, we see that everything is basically, the predominant deformation is the transverse shear, as you can see here. Okay, so basically this is telling you that when you do this kind of micromodeling, what is actually very important is the treatment of a nonlinear transverse shear. Now in this case, this is possible because our constitutive model is 3D, and the shell that we are using is a thick shell. So a thick shell has treatment for the transverse shear. The transverse shear goes to the material model, and the material model can handle it in a nonlinear fashion. Okay. That's why at the beginning I was saying you have to take care about what kind of shell element you use. Because for example, in this example, if I use instead of this, the thin shell, I will not obtain the same results, even if the wall seems to be thin, okay? And I will give you an example of what is happening. Oh, and take care that in this example, the bricks are not failing, only the mortar joints, okay? Now, if I go back and I change the shell element from MITC to, let's say, shell DKGQ. The DKGQ is a shell for thin plate analysis. So you may say, okay, I think it should work, but let's see what happens. So already here, you're a lot above the reference curve, and not by a small factor, by a lot. Then we are going to see, as soon as this finish, we are going to see why is this happening. So we just changed the shell from thick to thin. So you may expect, well, but the thin shell theory should be better for a more flexible shell. But here we will see a problem. Okay, let's let it run. Okay, finished. Now let's go back to the post processor. Now in this case, you remember that the surface was failing in the out of plane direction, creating transverse shear deformation. Now in this case, it's going to be different. Let me reload it. Okay, and here let me put the deformation to 10. Okay, and let's see how this one is deforming. So the overall curve is completely different, is much higher. Why? Because actually the thin shell is much stiffer than the thick shell in this kind of example. Then I'm going to explain you why. But first, have a look at the deformation. It's completely different. And as you can see, the mortar joints are not failing in shear as before. Why? Because of course this shell is not giving the material any transverse shear. And the material is actually converted into a plane stress material. So the strain in the out of plane direction and the stress are zero. Instead, and then what happens? Since the mortar joints cannot fail in the out of plane direction, they will be much stiffer, and ultimately the failure will happen also in the bricks, as you can see here. Basically, let me switch on the mesh edges. Here we see complete lines making the entire wall failing both in mortar joints and bricks. Why? Because of course, if the mortar joint cannot fail in the out of plane direction, they cannot create a complete crack. So the crack should pass through the brick. So basically, it makes the mortar joint much stiffer than the other. And so you can the only failure that you can see is a bending failure, not a transverse shell failure like it happened in the thick shell theory. Let me see. We have a question here. Okay. No. And so why is this happening? At the beginning, we said that a thin shell element can be used when the ratio between the thickness and the typical size of the plate is less than 1/10. And in this case, it is less than 1/10, but only if we consider the typical size of the wall as one of the sides. The problem is that when people in finite element talk about the typical size of a domain, they do not refer to the entire structure actually. They refer to the typical size in which the displacement field remains continuous. Now in this case, the displacement field has high jumps from even in the dimension of a single mortar joint. This is due to the fact that the two materials are completely different, and that, of course, there is strain softening. So the entire strain gradients are trapped into the mortar joints. The mortar joint instead has a typical dimension of 10, which is less than the thickness. That's why in this case, the thin plate theory does not apply. I think we have another question here. What is the interaction between the mortar and the brick? In this case, I mean, do you mean in this case or in general? What is the interaction between the mortar and the brick? I mean, I don't understand okay, in this case, the interaction is that basically the same as before. The only problem is how the finite element is sending the strain to the material. The finite element, in this case, since it is a thin shell, it assumes that the out-of-plane shear deformation are negligible. Since it is assumed that they are negligible, they directly send 0 to the material as a transverse shear. And of course, the material does not receive any transverse shear, and this transverse shear will not create any damage in the material. But as you have seen before, the transverse shear in this kind of example is much higher than the other strains. So that's why here the mortar joint is not failing as before. So basically, in this example, you cannot see one brick that breaks over the other in the transverse direction. The only thing that you can see is a bending failure, like this one. For example, here you see a straight hinge failing in just pure bending, and the same here. You don't see the kind of failure that you have seen before. And in this case, the damage will be both in the mortar joint and in the bricks, as in this case. Let me show you. If I go not to the vector plot, well, if you see the vector plot, you will see that there is no shear deformation. So let me animate this one. You see the vectors, they remain in the plane of the shell. Here, there is no transverse shear deformation for them, okay? That's why basically you see pure bending. This is the kind of plot that you see in a pure bending problem, okay? And if we look at the damage, in the previous example, there was no damage on the bricks because everything that was damaging were just the mortar joint. Now, in this case, instead, it is not like that because the mortar joint, since they cannot fail in the out-of-plane direction, they become much stronger than they were before. And the crack should find a path also through the bricks. So in this case, as you can see, mortar and bricks are failing, all of them. And then when the crack goes in the diagonal direction, both bricks and mortar, like in this case, this is a brick that has failed. Mortar, brick, and basically all of them have failed. So remember that if you are doing micromodeling, the typical size of this kind of wall is not a wall, is the size of the mortar. So in any case, it will always be a thick plate theory, okay? You got another question? Okay, perfect. Okay, so with this point, I told you about the difference between a thick shell and a thin shell. Just another question. Does it mean we should always use thick shell theory? Yes, for two reasons actually. In case of micromodeling, you should always use the thick shell theory. Why? Because I told you there is a huge difference in the material parameters. So the displacement will never be completely continuous. And there is damage. So since you have a strain localization, this strain will localize into the dimension of the mortar joint. So the typical size, in fact, because when the people started talking about the plate bending theory, they was referring to the standard finite element method. Now, in finite element method, there is one basic assumption that the displacement field should be sufficiently continuous. Okay, that was one of the basic assumptions of finite element. The problem is that when we use strain softening material, we are actually introducing discontinuities. The strain field is not continuous. In fact, you see that the deformation are completely inside the thin mortar layers. So you should reformulate the concept of what is the typical size of a plate. In this case, the typical size of a plate is the thickness of the mortar. And the thickness of the mortar in this case is 10, while the thickness is 110. So in this case, if you use micromodeling, use always the thick shear theory. This is the first point from a theoretical point of view. From a practical point of view, I would always use the thick theory in any case, just because of one reason. The thick shell implemented in OpenSees has a special treatment for the out-of-plane bending that works both for thin and for thick shells. So in any case, yes, use the thick shell theory. Unless you know that you are doing a particular benchmark and you want to test the Kirchhoff law of shell theory, you can use the other. But I will always use the thick shell theory, yes. So now we can go back to the thick shell. And I want to show you something else. Let me go back to the shell MITC4. I want to show you something else. When I told you that in this example, they were trying to understand the effect of the vertical precompression. And in the second step of the analysis, right here, we decided to fix the top displacement as they did in the example. So they first apply a vertical force. The wall will displace vertically here. And then before running the horizontal analysis, they fixed the vertical displacement at the current position. Now, since we realized that in this example, even if the overall failure is in out of plane bending, the local failure is in transverse shear. Now, as you know, material models such as frictional materials, such as the one that we use in the mortar, has the phenomenon of dilatancy. So when it is loaded in shear, it uplifts and creates an apparent increase of volume. Now, what's the problem is that in this case, since the vertical displacement is fixed, while the mortar joints are failing in shear, they would like to uplift the wall, but the wall cannot uplift, so it will create a vertical reaction, okay? So we need a parameter. I told you that here in the constitutive model, we have a parameter that can allow you to control this amount of dilatancy, which is the M1 parameter. And as I told you, if we go back to the paper, a value of 0 gives me the largest compressive surface. Let me go back to the definition of the surfaces. A value of 0 gives me the largest surface in this tension compression quadrant, while the values of 1 gives me the smallest possible section here. So what does it mean? Here I have the maximum dilatancy, here the minimum one. There is not a fixed number, so you need to calibrate this parameter based on experimental test, which is what we have done in this example. So I just want to show you the difference. What happens if I put this to 0, so I increase the dilatancy, okay? And I run the analysis with the thick shell, okay? Let's let it run. You will see basically that the total strength will be overestimated. Not that much as the thin shell, but it will be overestimated. It is already visible. So it was failing around 4.55 more or less, and here it is failing around 8. Then we will see the opposite. We will use the minimum dilatancy, putting that parameter to 1. And then in the post-processor, we are going to see how the total vertical reaction changes from the first step to the other when we change this dilatancy parameter. So basically, this is one parameter that you can calibrate using simple shear test on mortar joints and measure the uplift. Okay, just a few seconds. Okay. Let's go back to the post processor and reload this process. Okay, then I go to the plot group here, and I want to extract the total base reaction, so you can see what changes from this analysis to the other. Okay, so I go in the front view, I click on extract chart data, and I want to extract results from nodes, and I want to extract results from all stages. So the first stage is where I apply a vertical force, then I keep it fixed, and then I keep the vertical displacement fixed. So while I'm loading in the autoplane direction, the internal reaction of the wall will create an extra reaction there at the bottom. So extract from all stages, and in the abscissa I will put the time step ID. And here I will measure the reaction force along the Z direction, so vertical direction. Next, I need to select all the points where I expect vertical reactions. Okay. Next, add. I can call this use the react button just at the bottom. And I use add. As you can see here, when you create a chart, you have the option to say, okay, but if you have multiple selections, like in this case, how do you want to treat the results? You want to keep them separated? You want to calculate the minimum, the maximum, the average, or you want to sum them all? I want to sum them all because I want to compute the total reaction. So finish. Okay, now as you can see here, I have a constant value at the beginning. Okay, so first analysis, this value is the reaction given by the force that I put at the vertical analysis, and then as soon as I push the analysis and I push the wall, there is the development of shear deformation and shear failure in the mortar joints. And due to the latency, but the wall of course cannot uplift, so it has to react with an internal reaction. As you can see, it has this value. Now let's see what's going on if I decrease. So I detach this one from the database, so I keep it here. And we go back to our model and we put it to the opposite value. So instead of 0, which is the largest latency, I put 1, which is the smallest one. Now in this case, I should expect the result to underestimate the experimental data. So let's run the analysis again. So maximum the latency was overestimating it. This is the minimum one instead. Now, in the meantime that this goes, you may ask, okay, but how do I calibrate this model? But first of all, you need some experimental results on what is the evolution of the latency angle in your material, of the latency. And of course, you need some experimental tests for this. Then you need to know how to put this data inside your constitutive model. Now, plasticity models, they can treat very well the latency problem. So you can just put typically the latency angle in a non-associated plasticity and you're done. But this model, as I told you, is a damaged model. It has some plasticity, but it is used in a simplified way. So you cannot directly input the latency angle. But as I told you, there is this parameter that can somehow control the latency. So how did I do in my test here? Basically, I had experimental test on the latency angle of a mortar joint. Let me find it. Numerical modeling here. Oh, should be this one. Okay, so here we have some experimental tests, and basically you can measure the latency, how it evolves with respect to the normal displacement and so on. And basically I reproduce the same, you can do a single element test, or you can do directly inside the tester in STKO. You apply a distortion, a shear strain, and you measure basically the transverse deformation, the uplift basically of the element. And then I did some tests changing that parameter and trying to calibrate this vertical reaction. So for example, here I was trying with the minimum value and then the value of 0.16 that was fine in this example. In the example of the paper, of course. In my example here, it was 0.5, the good value, okay? So you just, the problem is that you just need to do some calibration for this parameter and you need some experimental test that you can compare to, okay? Okay, this is fine, it's done. The curve should be underestimating the experimental results, okay? And I will try to reload it and see what is the evolution of the vertical reaction in the other model. So whenever you, by default, this one is linked, okay? So when you reload, also the graph will reload, okay? But in this case, since I want to do a comparison, I unchecked the link to the database. So this graph will not update according to the database because I want to compare it with the new one. So reload, this one is remained as it is. Then I extract once again another data, always on node, all steps against the time step ID, reaction force along the z direction. This selection is already there, and I can call it reaction bottom P1 equal to 1. I don't want to create a chart. Okay, I can superimpose it here. Okay, as you can see, at the beginning it is the same, of course. Okay, because the top of the wall is not fixed. So for equilibrium, it is equal to the imposed vertical load. Then this wall is this top wall is kept fixed. And while there is a shear deformation, also here you have some dilatancy, but it's not that much, as you can see from here. So whenever you have a wall that is fixed and while loaded in shear or loaded in out of plane, that, as we have seen, generates a lot of shear in the mortar joints, transverse shear in this case, not in plane shear, you can expect this kind of behavior. So try to calibrate that material parameter, okay? So for I think we have a question, yes. Also the in-plane, of course, as we have shown in the previous example, it was happening also in the in-plane, but in this case, yes, it's happening in the out-of-plane transverse shear. So whenever you have shear and your model is fixed, cannot uplift, that parameter for the latency is quite important. So try to calibrate it properly with experimental results. Okay, so for this wall we are fine. Now I think I will show you some extra examples, and then we will leave the last, I don't know, 30 minutes for any doubts, questions, if you have any requests, okay? So now I will show you some other material, because yesterday someone asked me if it is possible to model the reinforced concrete shear wall using not the concept of a smeared reinforcing layer, as we have done, but if it is possible to use physical beams or trusses instead of that layer of the shell. Of course, it can be done. Now, I didn't have time to prepare an example for that, but we already have an example of a three-dimensional analysis of a column where the rebars and the stirrups are modeled as beams and trusses. Now, I will not try to replicate the model now because we don't have time, but I will show you how the model looks like. If you want, I can send also that model, and I will show you the results, okay? So for that reason, I want to save this one. Oh, remember, when you watch the video and you will see the file that I sent you, you will find probably some difference, because when I was running the analysis with the 0.5 here, there was some difference. It was not symmetric, so probably I wrongly set up the pattern here. But anyway, follow the video as a conceptual framework and look at that file that I sent you, because it's the correct one, okay? So here, probably I was in a hurry and I made some mistake. But it is fine, the concept is that. So now I want to go in my other computer, because that model was slightly larger than I was using the another computer, so I need to connect to the remote desktop there. And I will show you that last example. Okay, it is here. So basically the example was this one, a simple test on a reinforced concrete column. And we decided to try it. Well, here you have all the material parameters, parameters for rebars, stirrups, and so on. And there was a cyclic example of this. Then we decided to model it as a solid element, to do a detailed modeling of solid elements with the rebars modeled as beams with fiber cross section, so you can consider the nonlinearity in the beams as well, and the stirrups modeled as trusses. Now the kind of model looks like this. Then I will show you the results. So it's a pure 3D model, and as you can see from the geometry here, you can do all the 3D models that you want. Here it was very simple. Actually, you just need to draw your baselines, then you get a face out of them like this one. Okay, and a planar face, as you have seen for the brick case. There is a question. Yeah, of course, here we are using the symmetry, of course, for simplicity. Then I will show you later on. And of course, when you have a basic face like this and you want to extrude them, in this case, I wanted to extrude according to the stirrups spacing. There is a specific command where basically you draw the extrusion line and then you do the sweep command. And this sweep command will extrude this face along the sweep line. So you have all the correct solids modeled. Then as you can see, the beams, probably it's easier if I show you from the top view. Yeah. Here we have a hole for the beam. Now, if you notice, all the geometry has been done properly for a structured mesh. So everything is a quadrilateral, even if not straight, but a quadrilateral surface. So it can be meshed with a structured hexahedral mesh. The rebars instead are not solids, but as you can see, they are simple lines, okay? Like this one. If I switch off the faces, you will see it inside. It's a simple line because we are using a beam element for this. And then you may say, okay, but why is it detached from the solid? Because in OpenSees, the solid has only 3 degrees of freedom per node. Well, actually, in any finite element, has 3 degrees of freedom per node, while the beam has 6 degrees of freedom per node. But OpenSees cannot handle 2 different elements that expect 2 different degrees of freedom sharing the same node. So basically, the node of the beam should not be the same of the node of the solid, okay? That's why we model it separately. And then we created this kind of interaction here, which connects, let me pick it, okay? This one, that as you can see, connects each point of the beam to the surrounding point of the solid. And this one has a special boundary condition, which is here, which is called beam to solid coupling. It basically is a kinematic condition that couples the master node of the beam that has displacement and rotations to the slave node of the solid in such a way that the node of the solid will displace according to displacement and rotation of the master node of the beam. So in this case, you're actually creating a continuity between them. Then, of course, we have all the other materials. For the stirrups, just a side note. For the beams, we had to create separate lines, as you can see here. I think we have another note here. In case we are using shell, yes, exactly. In case you're using shell, this is not required because a shell has 6 degrees of freedom. So you can directly use, as I'm doing now for the stirrups. So for the shell, you can do what I'm doing now for the stirrups, also for the beams. So in this case, the solid has a different set of degrees of freedom, so I had to create the beams here, separately from the solid. But then when it came to the rebars are modeled with trusses. As you can see here, I'm going to select them. Are modeled with trusses, and for them, I didn't create extra line. I just assigned the truss property to the edge of the solid, okay? Now, in case of a shell, you can do the same also for the beam because the shell has 6 degrees of freedom. So you can directly assign the beam section to the border of the solid. you don't need to create an interaction as we did in this example. So then the note here was perfectly correct. So in case of shell, as Miguel Pereira was asking, you can directly assign the shell property directly onto the shell edge. Basically, is what we did, in fact, in the reinforced concrete shear wall example. I've drawn the shell and I assigned the lateral boundary beams directly on the edge of the shell. I didn't create an extra beam, in fact. Okay, here I can do it only for the trusses, because trusses can have both 3 or 6 degrees of freedom, so it is safe to assign it. Okay, so if we go on, well, of course, then you have a set of boundary conditions, of course, here. You have to fix at the base, vertical forces, horizontal imposed displacement on top, solid coupling, and then you also have the symmetry condition, because in this case it was symmetric, so we took advantage of the symmetry condition. Let me show you the property, how it looks like. So here in this case, we modeled the bottom and top steel plates, and then, as you can see here, all the solid. Here we took care of assigning a different material property around the rebar to simulate the fact of the adherence between the steady rebars and the concrete, because of course you cannot model this kind of way. You cannot model the cohesion of the rebars with the solid. And here you can see all the extrusion. You can see all the rebars, the stirrups, and so on. Of course, this is like this because we are using asymmetry. Probably it's easier if I switch off. Yes. Okay. You can see all the details. Okay. It will take a little bit of time to model this one, but it's not that difficult. It will take probably 1 or 2 hours to do a modeling if you are doing it for the first time. Then it will be much faster. And the analysis of this with just 4 processor took something like 12 minutes, not that much. And I'm going to show you the results. Okay. So this is the kind of result that you can expect. The basic one can be the surface color map. Then I will show you a video. Surface color map is basically whenever you see some results on the surface of your model. We have been using the surface color map on all our examples in the previous webinars and today's webinars. We have never used solid in this webinar, so I didn't show you the volume color map. The volume color map is the same as the surface color map, but very useful for people doing analysis with solids, because it's the same as the surface, but you have an extra parameter here that can calibrate the amount of transparency. For example, here I'm saying the maximum results is colored in red, the minimum in blue, but the maximum results is completely opaque, while the minimum result is transparent. So in this case, you can, for example, if I want to make it more transparent because I want to also visualize displacement up to a certain level, I can calibrate the transparency so I can see actually what's going on inside my model, okay? With this kind of volume plot, which is quite interesting for people doing, well, it is typically used for people doing solid structure interaction because they always work with solids. But in case you do detailed analysis like this, it can be useful as well. For example, here you can see the level of damage, for example. In this case, I want to say, I don't know, I want to visualize only the damage from a certain level to 1, so I can move this one closer to the white value in such a way that I can create a threshold and say, okay, I want to visualize only certain levels of damage. And this is quite useful for this kind of visualization, so you can see the developments of damage. And then, of course, you can do many other tests. And I will show you just a video in which we superimposed many plots, because, of course, you can superimpose plots. That's why the concept of plot group. Here, for example, I'm visualizing one plot, then you can create another one. For example, I want to see a vector plot of the displacement superimposed to this one, and you can do it. You can compose everything. So, for example, you can do some video like this. Let me find it. Here it is. Here, for example, we are superimposing the displacement we are superimposing first an undeformed shape here. So you can see actually the deformation versus the undeformed shape. Then we are using a plot for the displacement using a volume plot, as I showed you before. Gauss plot for tensile damage, which is this one, these black dots here. and then a Gauss plot for the rebars, showing only the deformation up to a certain level, so you can see where this deformation of the plastic hinges, the plastic deformation in the beams. So it can be pretty nice. Then you can do some animation on the plots. So the main reason of plot groups is because you typically want to compare different results, so you want to create some composite plot. So you can create more plots in the same plot group with different components and see how they develop together. Okay. Here you can see clearly the formation of the plastic hinge here. We have a question. Can the legend be fixed? Yes, it can be fixed if you fix both values. For example, in this case, we fixed it, the damage, we fixed it from 0.98 to 1. But in this case, we fixed only the minimum value. Here, we didn't fix anything, for example. Here, only the minimum value, and if you see, only the top value changes. In the damage, it doesn't change anything. So, sorry? Oh, probably there was a microphone on. Okay, yeah, so you can fix the legend, but only if you fix, let me show you, if you fix these values, okay? If you fix the minimum and the maximum, the same thing will happen in the legend, of course. If you don't fix it, the legend will update accordingly. Okay. One more question. Okay, then we have some, of course, now we have 30 minutes for questions. And so if you have any doubts and questions, and then we have many plans for the future. One thing that I've shown you something. I told you about the fact that STKO can be scriptable. You can find it also in many tutorials. Basically, everything. Probably I only told you, but without explaining you too much. But if you go, basically, if you take the preprocessor, everything that is here is a CAD and is built inside STKO. But then from definition down to the analysis steps, so all these components that, if you notice, they all have the same interface, which is this one, where you choose a model, you set the attributes, eventually you have some tester. But if you have a look, they are perfectly equal everywhere. So name, model, attributes, down to the analysis steps. They're basically scripts in Python. This is the nice thing about STKO, that it can be scripted by you. If you know Python, and if you know the API that we exported from STKO to Python, you can actually interact with STKO and create your own custom utilities. Now, just to show you that it's not a closed code, if you go on the installation folder, which is C, program files, STKO, here you have a folder called external solvers. And inside them, there is OpenSees. Now here it is full of Python scripts. So for example, physical properties, materials, Unixel materials, and you can see, for example, I want to know how do they code the concrete 01. You can open it and you can see it is a simple open source Python scripts. So if you know something about it, you can fill these things, you can change them, you can interact with OpenSees, with STKO basically. So all these things are basically the connection between STKO and OpenSees. Everything is done in Python. So for example, imagine you have your own OpenSees version and you add your own material. Of course, you cannot find it in STKO because we are not aware of the fact that you added a new material. But if you want to make it used in STKO, you can just create your own Python file, you put it there, and you will be able to use it through the STKO interface. That is a first approach. Then you can use the same Python interface to create automatisms. For example, in the first example, I've shown you how to create the automatic confinement. That, for example, was not done by us, but it was done by a user that was able in coding in Python, and he learned how to do it inside STKO. So he created that functionality. And you can do the same, basically. For the future plans, we are going to add also this capability to the post processor. because now only the preprocessor can be scriptable, but in the near future, also the post-processor will be. So through Python scripts, you will be able to access the database, create custom results, custom plots, and then make everything more automatic. So now if you have any questions before closing this webinar, please, any question or any doubt. And of course, if Professor Barum or Professor Oliveira, if they want, well, thank you everyone, of course, for allowing us to have this webinar, and thank you to everyone for participating. I don't know if Professor Oliveira or Professor Barum, if they want to say something, or if someone has some question, please go ahead.
Actually, I have a small question.
Yeah.
Massive. Thank you for the webinar. It's really nice. I saw there you can find in STKO the TC3D material in 2 places.
Yes.
Is there any difference between choosing the plugin or?
No, there is no difference. The only reason why you have 2 places in which you can find STKO is because before we put the damaged TC3D in our own version of STKO. Now we put the same, but in a form of a plugin in the new version of OpenSees. So they're actually the same. They just point to the same material. We left the old one just because for backward compatibility. So if you have a file in which you use the damaged 3D, not in the plugin session, now it will still work because it will call the one in the plugin session. It's just because we had to move it from in the source code of OpenSees. So don't worry about it, you can use either one.
Okay. And then I had a question about like the geometry. When you are doing some geometry in STKO, you use SU faces for the faces for planar faces and so on to basically merge different surface and like merging the edges mainly or nodes. Which is the parallel of doing the same with the solids, like function? Or there's many probably, or there's some.
There are actually 2 kinds of approaches for solids. It depends on what you want to do, and I'm going to show you because there is a main difference. Let me share my screen. Here. Okay, let me go back because here I'm controlling another computer. Okay, so this one I can close it, and I can go back to my own. Okay, so we create a new file. Okay, so those are basically the SU phases. So let me show you. Here we have all the Boolean operation. Okay, so typical operation to join things together or to create interferences between geometries are in Boolean operations, which are merge, unit, subtract, and intersect. Then there are 2 simplified specific ways for other kind of geometry, which is SU phases or make wire. They basically just join faces or edges, so they are faster, but they are not as generic as the merge ones. Okay, so if I want to merge 2 faces, you have seen that I can use the SU phases or the merge without any difference. If I want to join the solids, of course there is no simplified way. The only way is to use the merge or the union, and there is a difference. Let me show you. For example, if I create 2. Let me create 2 parallelepiped here. Okay, so this one is a solid, and you can see from the symbol here. If you're interested in knowing the geometry, each geometry has some subgeometry. For example, in this case, I have 8 vertices. I will have 12 edges, 6 faces, and just 1 solid, of course, the solid itself. Since it is just 1 solid, this is a solid. Okay, now I do another one just by copying it, for example. Okay, now let's say if I want to merge them together. Now you have 2 choices. you can either use the union operation, but if I use the union, here is what happened. The resulting is a solid, as you expect. But then what happens, for example, if I want to assign a material to this side and a different material to the other side? I cannot, because there is only one solid. In fact, if I watch it from the property, well, here probably is not so easy to visualize because you have these lines, but you have only one solid, because the common face that was here has disappeared, because due to the union, the common face is dropped. Okay. Now the other option, instead, here you can see that now there are two faces. The other option is to use the geometry. So that Boolean operation, the union, was fine if you had to assign just one material. Okay. If instead those are two physical separated geometries, but sharing the same nodes, you can use the merge command. The merge does the same, but without removing the common parts. So I take this one and this one, right click. And as you can see now, the symbol is different. It's not a solid, but this one is called comp solid. In fact, it has two solids, 1 and 2. They share the same node, but the phase between them is still there. Okay. So probably this one, it's easier to visualize if you do it with spheres or something else. But as you can see now, here you have two phases, one pointing here and one pointing in the other side, but sharing the same node. Now, in this case, you can assign two different materials. So this is the main difference between phases and solids when you do Boolean operation. The merge command, as I told yesterday, is much more powerful than this, because for phases, let me go back to the phase example. For phases, when you have phases like this, let me create the first one, and then a second one. Now here it is the same if I use these two phases, because the two edges are already overlapping. I just need to join them into a single edge, okay? And if I do the same with the merge, so I select both of them and I do merge, the result is perfectly the same. Now there is a difference. If I want to do something like this, and then I want to cut a line, I don't know, from here to here, and then I also, let me remove the 90-degree operator, okay? Let's imagine this is a beam that passes through these slabs and then goes outside. Okay, I cannot use the two faces here, because if I use the two faces, it allows me only to select the faces, not this one. The merge instead is much more powerful. With merge, I can select anything and it will create intersection between anything. Okay. Now the result is, since it is mixed, it has both faces and a floating edge. It is called compound. But if you go inside, you can see that it has 4 faces, some edges that are shared between them, and a free edge that is here. Okay. So the merge command is much more powerful, but take care that when you have to do large Boolean operations, like in our micro model, using the two phases is much faster than using the merge. Okay.
Right.
Is there any other question?
Can I ask one question?
Yeah.
First of all, thank you very much for your very nice and useful presentation. I have one question. Like you mentioned that in micro modeling, we will have we should use always the thick shell theory. But what if we do the macro modeling for masonry or for infill walls or something? Does it impact the considering the thin or thick shell theory, or it will be the same, because now we are doing macro modeling, not micro modeling?
Yeah, as I told you, I would always use the thick shell, because you never know how what will be the fracture band of your model. But if you're doing a micro model, the difference between the thick and the thin shell will be much smaller, because what in the micro model was seen as a transverse shear deformation will be seen as an overall bending failure in the macro model. Okay, so if we let me go back to probably you can see also in my paper here. I have a paper from the out of plane. While I was doing exactly that, just to show you the difference in terms of deformation. The one reference and the out of plane. Here, for example, I was using another method for transitioning between micro modeling and macro modeling, which is called homogenization. But the concept more or less is the same. So at the microscopic level, I was using what it is, the representative volume element, so micro modeling. And then at the macroscopic level, I was using an homogeneous model. So what this failure here looks like a transverse shear failure, which it is in a micro model. It can be seen in a macro model as an overall bending failure, because of course in the macro model you don't have an explicit difference between mortar joints and bricks. And so what happens in the continuum case would be like this. Let me show you. Which is this one. As you can see, you don't see the this, of course, this out of plane shear failure, but you will see it as a tensile failure, okay, as a bending failure. Sorry, it's perfectly the same. So it will not play that much of a role. The problem is that when you go under large deformations, so later on in the analysis, when you will see a localization like this, then probably the thin shell theory will not work so much, because then you have a narrow band. It's not as narrow as the mortar joint, but it is still narrow, so still smaller than the typical size of the plate. The problem is that whenever you have to do with damage and strain localization, I would always use the most general purpose approach. So if for a shell you can use a thick shell, I would always use that. So the difference will be much less than what we have seen in the micro model. But since the thick shell in OpenSees is more general, and it is valid also for thin shells, I would always use that, okay?
Okay, thank you so much.
I would like also to pose a question. I thank you also for the presentation. It's a very simple question. If it's possible when using bars to do line plots, for example, bending diagram by bending moment diagrams instead of the surface plots.
Yeah, actually now we don't have it, but we are working on it because many have asked it. For the moment, you can only visualize as it's in the Gauss plots, so you can see the bending moments and transverse shears as Gauss plots. But we are going to put it in the next 2 weeks, so always stay updated, because in these days we are making a lot of updates to STKO.
Okay.
So of course now you have this STKO. As I told you, you can ask us for extra 2 months of trial, but of course you can check the website and download any new version, because the license will be the same. So you just install the new version whenever there is something new.
Okay. And also one other question: is it? I believe it's possible to export the results to, for example, CSV files or for an Excel spreadsheet.
Yeah, all the graphs, they can, when you copy them to clipboard, they are ready to be pasted into Excel.
Okay. Okay.
And the graphs can be exported to PDF if you want, or the tables can be exported into CBS, of course.
Okay. Thank you.
Is there any other question? So of course I would like to thank everybody, and Professor Oliveira and Professor Varun for letting us do this nice webinar. And please, if Professor Varun would like to add something.
Yes, thank you, Massimo. First and all, thank you to you and to Guido for all the effort you put in the organization of this course. The feedback that I have been receiving these days was very positive, so thanks to you. I would like to thank also to all the participants for the interest in the course and for assisting it. And we, as organizers of this course, will be in touch with you. We'll keep you informed about next activities, next courses. And nothing in the name of the University of Porto. I'd like to thank colleague Daniel Oliveira from the University of Minho, Guido Camata from University di Pescara in Astia, Giorgio Monti from University of Rome, and from the EOS Association. and particularly also to you, Massimo. Thanks a lot for all the effort you put into organizing and giving this course. So thank you to you all, and hope to see you soon.
Of course. Thank you, everybody.
Just to take the words from Umberto and make them mine as well. So thanks so much, Maximo, for the very clear presentation. I got really impressed, and I think in the near future, we have a lot of people, guys from Masonry, working with these tools. I think they are very powerful. So we're very happy. And now, as Umberto said, let's see what we can do more in terms of additional education on these topics. Thanks so much.
There are many other things to talk about, so we can definitely organize many more webinars. So thank you, everyone, once again. Thank you for joining this webinar.